All right, in this video, we're going to look at a modified form of the divergence theorem, which is what our book calls the divergence theorem for hollow regions. Okay, so suppose the vector field F satisfies the conditions of the divergence theorem on a region D bounded by two oriented surfaces now. We have S1 in yellow sitting inside S2 in blue, and D is this region bounded by these surfaces that's shaded in white here. Okay, and we're going to let N1 be the outward pointing unit normal vector along the surface S1, and N2 will be the outward pointing unit normal vector along the surface S2. And what the divergence theorem for hollow regions says is that the total flux of a vector field F throughout the solid region D, that's equal to the outward flux through the outer surface S2 minus the outward flux through the inner surface S1, or put another way, plus the inward flux through the inner surface S1. You can think about just taking this negative and moving it inside, okay, and considering the normal direction minus N1, right? So now we're thinking about inward flux as opposed to outward flux. Okay, so why is this true? Well, if you first consider the scenario where we don't have S1, in other words, you just consider S2 in the solid region that it encloses, well, the divergence theorem there says that the total flux through that solid will equal the flux just through the boundary S2. All right, so now if we do have S1, think about fluid entering into the region bounded by S1. Right? Since our convention is to measure flux as positive if we exit a region and negative if we enter a region, then the fluid entering through S1 will contribute a negative flux, right? Because it's exiting this region D. And that's why here we're subtracting this yellow integral. Okay, so now this is really similar to what we saw with the modified form of Green's theorem back in section 15.4. Here we have a region enclosed by two simple closed curves. And for orientation, we said that that this region in white should always be off to our left as we move along any portion of the boundary. So if I'm on this outer portion of the boundary in blue, I should be moving counterclockwise. So this region in white is off to my left. But if I'm on this inner boundary portion in yellow, I should be moving clockwise. So the white region there is off to my left. Now another way I can phrase that is in terms of the unit normal vector. Okay, so uh, we chose the unit normal vector with respect to the orientation of the boundary curve. So the vectors n and then t, the unit tangent vector, which is just indicating your direction of motion, and the vector k, right, which is just the basis vector, points in the pure z direction, right? These three vectors form what's called the right-hand frame. In other words, if I take the normal vector n and I cross it with the unit tangent vector t, then I get the k direction, okay? So here, if I'm going to choose a normal direction, if I'm going to be moving counterclockwise, then I should be choosing the outward pointing normal, right? Because if I take n cross t, then I'm going to get positive k. All right, but now if I'm on this inner yellow boundary curve, right, if I take n1, right, which is the outward pointing unit normal vector to the yellow curve, and I cross it with the unit tangent vector t1, which is telling me the direction of motion, and right, since I'm moving clockwise now, it's pointing in this direction. See, if I take n1 cross t1, I'm not going to get k by the right-hand rule. I'm going to get negative k. So here it actually is appropriate to take as your unit normal direction negative n1. In other words, the inward pointing unit normal vector, and that's essentially the same convention that is being followed up here. All right, well, that's going to do it. In the next video, we'll go ahead and illustrate this modified form of the divergence theorem, and I will see you there. Thanks so much.